If we are finding f dash of x when f of x is a power of x, that is x, x squared, x cubed and so on, we compute, as always, the limit as h tends to 0 of f of x plus h minus f of x over h. That is, we compute these quantities, so when f of x equals x, we compute the limit as h tends to 0 of x plus h minus x over h. When f of x is x squared, we compute the limit as h tends to 0 of x plus h squared minus x squared over h. And when f of x is x cubed, then we compute the limit as h tends to 0 of x plus h cubed minus x cubed over h. And in doing so, we expand the expressions x plus h squared, x plus h cubed, and so on. Now, since all of these expressions have the same general form, we can do all of the work in one go if we can expand the expression x plus h to the power n, where n is an integer, i.e. where n is in the set n, where n contains 1, 2, 3, 4, and so on to infinity. And that's because in order to find f dash of x if f of x equals x to the n, we have to compute the limit as h tends to 0 of x plus h to the n minus x to the n over h. And so the question is, how can we write down the expansion of this quantity x plus h to the n in a useful form? And the answer to that question, use the binomial expansion. So what is the binomial expansion? Well, it allows us to write down immediately the expansions of terms like x plus h squared, x plus h cubed, x plus h to the 4, x plus h to the 5, x plus h to the power n, where n is an integer, i.e. where n is a member of this set 1, 2, 3, 4 up to infinity. And by immediately, we mean that we don't have to multiply out all of the brackets using crab clause or the FOIL method, which can be long-winded and tedious. And the binomial expansion tells us that x plus h to the n is this long and complex expression shown here. The terms in the blue boxes comprise products of powers of h and x. And you should note that the powers of h and x always add to n. The expressions in the green boxes are numbers, and in fact they are numbers called binomial coefficients. Now in fact we don't need to know how to compute these, but if you are interested, there is a formula shown here, or there is a method called Pascal's triangle that allows their computation. I won't discuss those in any detail in this video, however. We do need to know though that the first number, read as n choose 0, is 1, and that the second number, read as n choose 1, is n. And that allows us to write down the expansion of x plus h to the n in the form that we require it, which is this expression shown in the blue box. And you should note that anything to a power 0 has turned into 1, and anything to power 1, such as h to the power 1, has become that term itself. So h to the power 1 becomes h. Here we see Pascal's triangle, which is a triangle of numbers which provide the binomial coefficients. And when we expand the various expressions such as x plus y to the 0, x plus y to the 1, x plus y to the 2, and so on, we get the following results using the binomial expansion. Which I have left in unsimplified form. And if you wish, you can check that those results are correct by expanding the expressions manually. And now we can proceed to the problem in question. Find the derivative of f of x equals x to the n, with n being an integer in the set n, from first principles. To find f dashed of x, we compute the limit as h tends to 0 of f of x plus h minus f of x over h, which becomes the limit as h tends to 0 of x plus h to the n minus x to the n over h, which turns into this long and complex expression when we expand x plus h to the n using the binomial expansion, with the expression in the green box being the binomial expansion of x plus h to the n, and we can subtract the leading and trailing x to the n to obtain this expression. And we note that each term in this expression has a factor of h, which we can factor out, which we have done here to leave a leading term inside the brackets of nx to the power n minus 1. And on dividing away the h from the numerator and denominator, we obtain this expression, the limit as h tends to 0 of nx to the n minus 1 plus other terms. And we split up that expression into the limit as h tends to 0 of nx to the n minus 1 plus the limit as h tends to 0 of all the other terms, i.e. we have turned the limit of a sum into the sum of limits, which we may do using a result from the algebra of limits. And that reduces to nx to the n minus 1 plus the limit as h tends to 0 of the other terms, which results from the fact that nx to the n minus 1 does not vary with h, and so is not affected by the limiting process. And now we note that each of the terms inside the limit expression has a factor of h, which we can factor out to the front as follows, to give us the limit as h tends to 0 of h times other terms, and we split that up to give us nx to the n minus 1 plus the limit as h tends to 0 of h times the limit as h tends to 0 of the other terms, i.e. we have turned the limit of a product into the product of limits, which follows from a result from the algebra of limits. And since the limit as h tends to 0 of h is 0, we obtain nx to the n minus 1 plus 0 times the limit of the other terms. And since the limit of the other terms is clearly a finite number, 0 times that limit becomes 0, and we finally obtain nx to the n minus 1. And so we have that if f of x equals x to the n, where n is an integer, then f dashed of x equals nx to the n minus 1. And from that general result, we can obtain the specific results for n equals 1, 2, 3, 4, and so on, as follows.